Hello everyone, my name is Azri Azhan 23002072, and my assignment is to make this video that explains how engineers analyze a combustion system. Today, instead of discussing combustion theory directly, we will look at how engineers analyze a combustion system step by step, from fuel entering the system until useful power is produced. Instead of teaching definitions first, we walk the audience through the process of designing and evaluating a combustion system. So, I will tell you how we will make it. For the first step is we need to choose the fuel. We have common fuels such as methane, octane, or more we know it as gasoline, ethanol, or coal. Selection is based on energy content, cost, availability, and environmental impact. So, the first step is choosing a suitable fuel. Engineers consider energy content, cost, availability, and environmental impact. Different fuels produces different amounts of energy and emissions. So, such as if we have the energy content is high but environmental impact is good, so we need to choose the best one yet possible. Choose the best. So, second step is after selecting the fuel, engineers determine the balanced combustion equation. This allows us to calculate how much oxygen is required and what products will be produced. So the basic equations is CH4 plus 2 oxygen is equal to carbon dioxide, and we'll get water also. Why balance the reaction? So we balance the equation because we will need to have the mass conservation. We will also need to calculate the air requirement, mass conservation, and we need to predict the product, which is the product prediction. What we will need or what we will produce from the reaction. So the product we get here is carbon dioxide and water. The third step is calculating the theoretical air requirement. Since oxygen comes from air, the amount of air supplied must provide sufficient oxygen for complete combustion. So we know that air composition is 21% oxygen and 79% nitrogen. So theoretical air is the minimum air required for complete combustion. We can also have excess air, but we will discuss a bit about it later. And then engineers then evaluate whether combustion is incomplete combustion. If the incomplete combustion, it will waste fuel and increases harmful emissions. So to make the perfect combustion, we need to have it to be a complete combustion. Complete is perfect, so it will produce carbon dioxide and water. If it is incomplete, it will have or produce carbon monoxide and soot and unburned fuel, so it is not good. It will just only waste your fuel and increase harmful emissions. Next step, we need to determine energy release. Once combustion is confirmed, we calculate how much energy the fuel can provide. This energy is represented by the heating value. So we have two types of value, higher heating value and lower heating value. For example, gasoline is approximately have 44 megajoule per kilogram. But what is the meaning of heating value? It is amount of useful energy from fuel. Amount of useful energy from fuel. So the next step, step 6, is to predict the flame temperature. We are using adiabatic flame temperature. The energy release raises the product temperature. Engineers estimate the adiabatic flame temperature to ensure equipment can withstand the operating conditions. So our application is the engine design, boiler design, and when we need to select the materials. So our work will be nice and perfect and efficient. For the next step is step 7. Evaluate energy efficiency. Energy input will produces useful work plus losses. It will always be losses if we input the energy. Losses that I mean including by the exhaust gas, heat transfer, and friction. Not all energy release become useful work. Some energy leaves through exhaust gases and heat losses, reducing the system efficiency. So the efficiency is reduced from loss. Step 8. Evaluate energy efficiency. While energy analysis tells us how much energy exists, AZRI analysis tells us how useful that energy is. This helps engineers locate inefficiencies. So, in terms of engineers, we don't need to look at energy. So, we need to measure the AZRI, because AZRI analysis measures quality, but energy analysis measures quantity. It is used to identify inefficiencies and irreversibilities. So, AZRI is good for engineers. So, the next step is, the next slide is an internal combustion engine is a good example. Fuel combustion creates high temperature gases that move the piston and produce useful power. Although only part of the fuel energy becomes work. Internal combustion engine. Fuel will become combustion chamber, and it will be high temperature gas. High temperature gas will move the piston motion, and the piston will make it useful power. For example, typical exergetic efficiency is equal to 40%. So the last one is final engineering workflow. In summary, combustion analysis follows a systematic engineering workflow. By completing these 8 steps, engineers can design safer, cleaner, and more efficient combustion system. So, there is only 8 steps, which is select fuel, balance fraction, calculate air requirement, check combustion quality, determine heating value, predict flame temperature, evaluate energy efficiency, and perform AZRI analysis, and then we will have perfect combustion. That's all from me. Thank you.